Hello everyone. Let us discuss about applying Wiener filter for filtering classical filtering problem. A signal d of n is to be estimated from a noise corrupted observation where x of n is equal to d of n plus v of n, where v of n is noise. Filtering or noise reduction is an extremely important problem in many applications such as transmission of speech in noisy environment or reception of data across a noisy channel, or it may be useful in detection and location of targets in sensor arrays, using sensor arrays, and the restoration of old recordings or the enhancement of images are the places in which we apply Wiener filter for classical filtering problem. What are all the assumptions to be made before starting this analysis? The first foremost important assumption is the noise is said to be zero mean noise, and it is uncorrelated. Noise is uncorrelated with d of n. The importance of this assumption is when you say noise is uncorrelated with d of n, the expectation of d of n and v of n is equal to 0. Right? That would be more useful. We are going to discuss about it. Right? And then let's start analyzing the cross correlation between desired to the input based on the assumptions made. So rdx of k is equal to e of d of n into x asterisk of n minus k. But n minus k, x of n minus k, what is x of n? X of n is equal to d of n plus v of n. So x asterisk of n is equal to d asterisk of n plus v asterisk of n. So x asterisk of n minus k will become d asterisk of n minus k and v asterisk of n minus k. So in this analysis, we have already made an assumption. Noise is completely uncorrelated with d of n, because of which the second term is made equal to 0. So obviously rdx of k gets reduced to rd of k. Great. So let us go to the next stance, where rx of k. What is rx of k? Rx of k is equal to expectation of x of n plus k multiplied by x asterisk of n. X of n plus k is to be replaced by its equation, because x of n is equal to d of n plus v of n. So x of n plus k will be equal to d of n plus k plus v of n plus k. Whereas x asterisk of n is equal to d of n plus v of n. So x asterisk of n is equal to d asterisk of n plus v asterisk of n. When we expand these two products, obviously you will get 4 terms, out of which 2 of them mean only the cross correlation. So obviously those two cross correlations will be made equal to 0 because of the assumptions. So obviously we get only 2 terms. That's why rx of k is now converted into rd of k plus rv of k. Right. Now with rd is equal to autocorrelation matrix of d of n, and rv is equal to autocorrelation matrix of v of n, and rdx is which gets converted to rd vector, rd of 0, rd of 1, rd of 2, rd of p minus 1. Now rx of k is equal to rd of k plus rv of k. With all these assumptions, is it possible to change the Wiener hopf equation? What is the general Wiener hopf equation? Rxw is equal to rdx. So Rx is replaced as Rd plus Rv into W is equal to Rd. So when we look into the modifications part, Wiener hopf equations meant for FIR Wiener filter, optimum filter, gets changed in the case of classical filtering issues. Rxw is equal to Rdx is now converted into Rd plus Rv into W is equal to Rd simply. So the modification of Wiener hopf equation when it is applied for classical filtering issues, noise reduction issues. Okay. The second important application is linear prediction. Linear prediction application will be done in 2 ways. One is with noise-free observation, the other one is noisy observation. Let's talk about noise-free observation. Noise-free observations based prediction, the desired output is x of n plus 1. Estimate of x of n plus 1. So it is x of n plus 1 cap in terms of linear combinations of present and the past samples. So x of n plus 1, which is equal to in this case the output of the Wiener filter when it is used as a linear predictor, d cap of n will become x of n plus 1 cap, which is equal to w of k into x of n minus k. What are w of k? W of k are coefficients of the predictor. K is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, k is equal to p minus 1. So let's think about rdx of k, how it gets converted based on the assumptions and other things. So let's see. rdx of k is equal to expectation of d of n into x asterisk of n minus k. D of n is actually x of n plus 1, x asterisk of n minus k. X of n plus 1 into x asterisk of n minus k, as you all know, it is only the statistics, second order statistics only between x and x. So it is rx of k plus 1. Okay, so rx now is getting converted, rdx is converted into rx multiplied rx of k plus 1. Okay, so the Wiener hopf equation now is modified. Instead of rxw is equal to rdx, now it becomes simply rxw is equal to rdx is simply converted into rx. rdx is converted into rx. In the matrix format, the changes are shown. Using those assumptions, now the minimum mean squared error in the case of Wiener filter used as a linear predictor equations are stated. Okay, rd of 0 now converted into rx of 0, and rdx is converted into rx of k plus 1. Okay, now there are two differences, noisy version and noiseless input. In noiseless input, giving x of n, obtaining the x cap of n plus 1 as the output is called noiseless observation. The first diagram we specify about giving x of n as an input to a Wiener filter, where extracting x of n plus 1 as the next expected output. So the difference between the estimate to that of the original gives me the error. So it is with respect to noiseless, whereas in the case of noisy version, x of n is corrupted by v of n, so you get y of n. When you apply y of n as an input to w of z, it produces the output because it is employed as a predictor. So it estimates x of n plus 1 cap as an output. So d of n is x of n plus 1. So d cap of n is equal to x of n plus 1 cap. So the difference is called d of n, noisy version. So y of n is equal to x of n plus v of n, and output equation will be written as actual output is given by the convolution of filter coefficients with the inputs. Now the input is only in terms of y of n, so w of k into y of n minus k will be the result for the equation used in the place of Wiener filter when it is employed as linear predictor. Okay, so x cap of n plus 1 is equal to summation k is equal to 0 to p minus 1 w of k into y of n minus k is replaced by x of n plus k, n minus k plus v of n minus k. So now the equation gets changed into rxw is equal to rdy is now converted into ryw is equal to rdy. Rxw is equal to rdx, ryw is equal to rdy. This is the change that is made, where ry of k, what is ry of k? Ry of k is equal to simply expectation of y of n into y asterisk of n minus k, which can be converted into rx of k plus rv of k. That you can easily understand, because when you substitute for y asterisk of n or y of n, you will find out there are 4 terms. So out of 4 terms, only 2 terms will be maintained. The remaining 2 terms will be cross correlation terms, will be replaced with zeros. Okay, ry of k is equal to rx of k plus rv of k. rdy of k is equal to the cross correlation between d of n and y asterisk of n minus k. We find out that this is equal to simply expectation of x of n plus 1 into y asterisk of n minus k, which can be again reduced to rx of k plus 1. So rdy of k is also reduced to rx of k plus 1. ryw is equal to rdy, can be even rv is equal to ry is equal to since both of them are uncorrelated, Rx plus Rv nu maaridu. So this can be finally written as the Wiener hopf equations to be used in the place of Wiener filter for Wiener filter to be applied as a linear predictor. Thank you.